Alright, so as we apply a force over a distance, and we keep adding up these little bits here, we get a change in the object's motion, because a force causes an acceleration, which means it's moving faster and faster every moment as it moves through that distance. And if you're going to move faster, it's because that means that you have more energy, and we have to do some work to get that energy. So the work done when the force is not parallel to the displacement is the component that is parallel to the distance times the distance. Okay, you have to have that parallel component. So if you have an object like a bag or something that you're holding, and you're applying a force up, but you carry it along the hallway so that the force and the displacement are perpendicular to each other, then how much work is done here? Zero work done by that force in the picture, because none of that force is causing the object to change. Let's take that idea of work being the force that's parallel to the distance times the distance, and look at your inclined plane of science. Okay? So from what we know about forces, if I were to pull the little cart up the incline, so no spring, we're going to start down here and we're going to pull it up the incline with some force pull at a nice constant velocity, so V is constant until we get to the top. What would the pulling force have to be equal to get the object to the top there as it goes from 0 along this delta x? What would the pulling force have to be equal to? You remember summing the forces in the x direction? So the force pull up the incline minus the component Fg sine theta down the incline would equal 0. So then the pulling force would be equal to Fg sine theta. So then how much work would that pulling force do? Is the pulling force parallel to the delta x?
Yes.
Yeah. So it would be Fg times sine theta all times delta x. And that would get it to this position up here, our final position. So Fg delta x sine theta. What's delta x sine theta equivalent to?
Y.
Yes, the height. And if Fg is the weight, that means m times g times h is equal to the work done by the pulling force. So then once it's up there and it's just sitting there, can it roll back down? Yeah. But in order to roll back down, it has to have some sort of energy that it can use. Just like if you're going to go somewhere in the car, you have to have gas in the tank. If it's empty, you no go. Right? So if you're doing work and pulling it up to a height, and what do we know about mass and energy in the universe? Oh, come on, you learn it. And
Can't be created.
Yes, it cannot be created nor destroyed.
Oh.
Can be transferred from one form to another. It can be, and it can become unusable as we dump a lot of energy into the atmosphere. Mass and energy. Mass energy. Yes. Okay, so the work you do is equal to this mgh. So the energy then stored because of the gravitational field would be mgh. Yeah. Would be equal to the work done by that pulling force. Now, let's look at what happens when a force is applied. So we have some net force. This represents all the forces in the horizontal direction acting on this object that's going to go a distance d. Okay? So the work would be the net force times the distance. But net force is equal to the mass of the object times its acceleration. So then work would be equal to, the net work would be equal to ma times d. Well, a lot of times d is delta x if we're looking at a horizontal change there. And so work is equal to ma times delta x. And a delta x reminds me of v squared equals v initial squared plus 2a delta x. Do you see that? So then that would be v squared minus v initial squared divided by 2 would be our a delta x. So could I substitute in and say that the work done is causing this mass to have a change in velocity?
Change in kinetic energy. Ooh.
So then the net work done on this object would be equal to, let's break it out, 1/2 mv squared minus 1/2 mv initial squared.
I feel like this is the second time you've done adjustments.
And so then, what are we going to call this? We get to put a name with it. It's moving. What's a word that means moving? Kinetic. So we call this the kinetic energy, which simply means the energy stored in the movement.
So work can equal potential energy or gravitational.
So that the derivation I just went through was just for an object that was moving along a flat horizontal change in position. Okay? So what if we look at an object that is maybe like going to move along this curvy x and y direction? First of all, does energy have a direction? No. Either you have it or you don't, or you gain it because you're adding energy to the system, or you quote-unquote lose it because energy is being transferred out of the system. Okay? So if we start up here, and let's say our little roller coaster car of science is up here, and we're having a good day. Whee! And we're going to ride the little cart down, but the ground is way down here. So this is where y is equal to 0, or h is equal to 0. Okay? Is there energy stored, if the little car has a velocity, v, is there energy stored in its position in the gravitational field? How did the car get up there anyway? Something had to pull it up there. The last time I rode a what do you call it? That kind of thing. There was a chain that applied some sort of constant pulling force up the incline, chugga 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 chugga. So the work done by the chain was equivalent to the amount of energy stored in its position, because from here I can move and go somewhere. So there's energy stored in the gravitational field because of its height, H1. Now, you've ridden on a roller coaster, but maybe you've just ridden on a hill or something. You start at the top of the hill, and what happens down here? Are we still going? Yes, that's what makes it fun, is that we're going like really fast, and your hair's like whoopee, and you're like, yay, this is fun, okay? And we're still going, probably even faster. Is that what you think? Even faster? Okay. So now what? How is the energy stored in the system in our second snapshot?
There's more kinetic energy than...
So think about it this way. There's energy stored in its position with respect to the ground, and there's energy stored in its motion. Okay, so we have both of those. Okay, and there may be more energy, and more of the energy is transferred to the motion. So if you think about what's happening before and what's happening after, and my system is what? What's your system going to be?
Earth.
The cart and the earth. So up here we have some energy stored in the position. I'm randomly I'm just picking this, and I'm going to call it E sub G. Let me just scroll back up here for 1 minute. So this was the work done to get the object to this height. So it became the energy stored in the gravitational field, E sub G. The work done by the pulling force in this case right here was equivalent to this change in kinetic energy. So delta means change, and that would be EK. So we can also describe energy stored in its motion as 1/2 mv squared. Let me put that back in there. And y'all like a box, so I'll throw a box around it. Okay. So then, is it moving? Yeah, a little bit. How many boxes you want me to give it?
3.
I heard 1, and that sounds good. Okay. So then what's going to happen on in the second snapshot? All right, how many EGs do you want?
2.
You want 2? All right, so then how many EKs should I have? So I got 1, 2, 3, 4, 5, 6, so that I need... And so I have kept up with all of my energies. So energy cannot be created or destroyed, just transferred from one form to another. And this shows that. It's all about the reference point when it comes to your energy equation. So right now, this says that EG, and I'm going to say at 0.1 plus EK at 0.1 would be equal to EG at 0.2 plus EK at 0.2. So this is the energy transformation equation. This is the energy flow chart. We like to call it LOL sometimes. And then this is the energy transformation equation. We created this energy transformation equation based on how the energy was being moved into or out of the system, or within the system itself. So this is the energy transformation. Okay.